Hi there. I'm Janet Bell with ERLC, and I've been poking around in the new computer science, organizing Idea in the new science curriculum. And I'm pretty pleased to be able to share with you some of the things I've been discovering and learning and becoming quite excited about when it comes to teaching computer science with kids as young as kindergarten, all the way up to grade 6 and eventually beyond. If you would like a copy of this presentation, and I sure hope that you would, please pause the video and scan the QR code that's just on the screen there, because that QR code, just scan it with your phone, that will open up a copy of the presentation. There are so many links embedded in this presentation that really the presentation is more about the links than the presentation itself. We're going to look at basically what is computer science, what is computational thinking, what is design thinking. These are concepts that come up again and again in the curriculum. And so I'd like to take a look and see what that actually looks like, where I have this expand section here. And then I'd like to hopefully to give you some assurance that you might be quite surprised to learn that you may already be teaching computational thinking concepts perhaps all the time, but without using the computational thinking vocabulary when you're talking about them. These are concepts that people know, but they don't really get because they don't have the right word for it when looking at it through that lens. So your takeaway, I hope, will be to be able to learn some of that vocabulary of computational thinking and use it with students. And then last of all, I'll leave you with some pretty big questions. How do we teach problem solving now? How can we amp up understanding using that vocabulary? How might computer science be already threaded, not just through science, but other curricular areas too? So that's where I want to go. The big picture, of course, is the world is changing. And there are all those quotes you've heard before, like, we're preparing students for their future, not our future, and, things like that. But the reality is the world is complex. And not only is there a sense that we need to be able to think like computer scientists and to be able to form that future, but there's also that whole ethical side of it as well, right? We need the people with who are reflective designers to be able to think, how can we shape our computer science projects for good in the world? There's such a big picture that we are preparing our kids for today. Our first definition is computer science itself. Computer science is a field of study. Computer science is a science, but it is a way of thinking as well when you get into that notion of computational thinking. Computational thinking is a problem-solving approach that draws on those concepts and methods of computer science and then applies them, but it can apply them far beyond computer science itself. So, for example, in everyday life, is if you're at the beginning of the day trying to plan your daily schedule, and to plan your daily schedule, you might decide, okay, first of all, I need to break down my task of my entire day and think, okay, maybe I've got some work chores, some household chores, and some leisure activities that I want to place into my day. That's going to be that decomposition stage of computational thinking. Pattern recognition is the second stage. And so in my schedule, I might say, well, I have some patterns. Like I know that if I get my email and stuff out of the way for the first part of the day, and then maybe a little bit of after school at the end of the day, that's going to work. And I can have these sort of sequences in place, and then I can jigsaw other things in between that. Abstraction, I might say, okay, I'm trying to plan my day, but there are things that I really don't have to do today. So I'm going to remove parts of my problem that are unnecessary and make one solution work for multiple problems. So I'm trying to get through a busy day. I really need to mount a new curtain rod upstairs in my house. But yeah, I could actually leave that till the weekend. I'm going to remove that and just have it look at only the things I really need to look at now. And then once I have all those, I've taken apart my problem, I've looked for those bigger kind of patterns. I've taken away the stuff, the extraneous stuff. Now I can design, this is what my day is going to look like. And that's an absolute example of computational thinking applied in real life, not doing coding on a computer at all. And so when you think with our kids, how often are you working with students and they're coming up to you and they're saying, I have this problem. And what's the first thing you're going to say is, take a breath. Now let's look at it. Let's break it down into its parts. Okay, what of these things are you able to do? What are the things that that we've sort of done before elsewhere? What of the things that kind of aren't relevant? And now, what are the steps we're going to take? We've all done that with students. That is computational thinking. What we don't do is use the vocabulary. So my suggestion to you would be decomposition, pattern recognition, abstraction. Let's abstract that and let's make an algorithm and use that along with our, other language that we use, just so that these words don't sound scary to people, because for adults too, they're big words. They sound scary, but they're really not. So the thing to remember with computational thinking, it's about becoming a mathematical thinker. It's not about becoming a calculator. And it's about operationalizing that thinking in the real world. So you're thinking like an engineer, or maybe even like a little bit like an AI bot these days. So you're thinking it, you're solving your problem, going through those steps, and then you're putting your plan into operation. You're making it happen. You're making it real. That's computational thinking. Now, design thinking is a little bit different. And I love how the two go together, but they're just so different from each other. So design thinking is an approach to problem solving that emphasizes empathy, creativity, and experimentation. And so if you've done any of those exercises, like here are 5 pipe cleaners and 5 paper clips, what can you make out of that you can use around the house? Those kinds of activities, those are design thinking activities. So these are activities that have you first think, what is a problem that I might have? Maybe I don't have a way to hang my dirty dish rags. And so you come up with your problem, you define it. Then it's like, what if I do this? What if I do this? And all the brainstorming, ideation, trying to solve my challenge. And then it's like, well, maybe I can use these pipe cleaners and these paper clips to create some kind of prototype that I can test and try out and decide if that's going to be the solution that I'm going to implement. So in design thinking, you're understanding your problem, you're exploring your solutions, and you're making it happen. So when I go back to computational thinking, you can see breaking something into its part, looking for patterns, getting rid of the extraneous stuff, coming up with a plan. This could be inside here, where as I'm testing my prototype, maybe I have to go through some computational thinking to do that, and vice versa. If I am putting together a plan to code a little robot to do something, or a plan to show my friend how to clean their teeth, just as a partner activity, non-tech in class, to do that, you might need to, at some part, think, okay, I need to go through this design phase in order to figure out how I can best go about doing this. So they're complementary processes that are very big in the new curriculum. And so when I think of how they relate to each other, very simply, computational thinking, you have all of this mess of challenge and problem, and you're trying to move in, kind of converge your way to your solution, which is your step-by-step instructions on how to do something. Whereas with the design thinking part, it's kind of the opposite. It's more like divergent thinking, where I'm trying to understand my problem. And it's like, well, I ideate, I could do this, I could do this, I could do this. And then eventually, yes, you come up and you implement a solution. So they're very complementary to each other. I wanted to share these with you. There is a link on the last image here that takes you to a website created by School District 61 in BC. On their website, they have these 4 graphics: decomposition, pattern recognition, abstraction, and algorithmic design. And they give all kinds of examples of how we're already doing it. So for decomposition, identify the instruments used in a song. What were the key events of the 20th century? What countries make up Europe? What information do you need to work out the circumference of a circle? So just those sorts of breaking things down into the part, the words break apart and pieces. These are the kinds of words you're using when you're talking about decomposition with your students. Pattern recognition, patterns, matching, any of those sorts of phrases, you're looking at pattern recognition. Abstraction is where we're pulling up from it. So your thoughts, your ideas, write a blurb for your movie, recreate the image, create a model. All of those things, you're pulling it up to that world of ideas rather than just breaking stuff apart. We're like, oh yeah, let's pull it up. And the last area is algorithmic design. That's your plan, right? So in early years foundations terminology, they call it the plan or call it instructions. And if you think of the new computing science curriculum, the word instructions comes up again and again in those early years. And so what they're doing is they're moving them through. Can we break this apart? Can we like match things, find patterns? What are we thinking here? What's important? What's our plan? That is computational thinking. You don't need a computer to do that at all. Now, in the computer science curriculum itself, instructions is the word you're going to see in those early grades. Creativity comes in grade 3. In grade 4, they talk about algorithm. And so we saw here that algorithmic design, that is the instructions, right? So this is where we're starting to use that terminology a little bit more mindfully in grade 4. And then in grade 5 and 6, we move into language of coding and design thinking. So if I just click here, this takes me to curriculum.learnalberta.ca. It takes me right to the science curriculum. So I'm just going to search for computational thinking across the entire curriculum. Take it down to computational. So even just the word computational, we have 45 results coming up in those first few years. If I look at the idea design, 98 results matching your search criteria. So we'll see science grade 4, science grade 6. And now just given even the words we've looked at, in what ways are abstraction, design, and coding related? So we've already talked about abstraction and design. Coding is the one we're going to look at in just a moment. So lots of connections, design and coding, computational artifacts. Design is sort of that through word that connects the different pieces together. And you'll see that the whole notion of designing and creativity and computational thinking is recursive across the entire curriculum and across many subjects and fits right into the competency progressions, because really what we're looking at with both design thinking and computational thinking is basic problem solving. And problem solving is something that we have thought about for years and taught for years, and it's just using that new language to it. Before I go, I do want to just dip into coding just a little bit. Coding is a concept that we still have an old way of looking at it. When we think about coding, we think about, the guy or the hacker, someone who's got all of these lines of crazy code and it's like out of some movie. But really, coding is back to that way of thinking again. So whether it is using a microbit, where you're just picking up like microbit, or a program like Scratch, where you're designing using block coding, or maybe you're just teaching a choose your own adventure book where people are moving to a different part of the book depending on a decision they make at a time, or whether they're writing a series of Google Slides where they're going to use that branching logic as well, so they can go to different places on the slide. That is all the same kind of thinking. That is still coding. And so computational thinking integration can happen in many, many ways, not just that traditional view of coding. And so if students are creating a game or an interactive text, that's computational thinking. If they're creating a story that they're animating using a program like Scratch or just in Google Slides, that is computational thinking. Playing Simon Says, where you do something on a certain input, but you don't do it on another input. Those are all examples of that kind of thinking. So my takeaway for you is please learn the vocabulary, learn these words: decomposition, pattern recognition, abstraction, and algorithmic design. And then you can use this chart to help you think about how we're going to use those words with the younger kids, break apart in pieces, patterns and matching, thoughts and ideas, instructions and plan. These are places where we can start. Some big picture questions to leave you with today. How do you teach problem solving skills now? How can you amp up understanding of computational thinking by using that vocabulary when solving problems with students? Question 2, where does computational thinking fit within the broader spectrum of everything we try to achieve as teachers and learners? And the same thing would be for design thinking. And last of all, how can conceptualizing this help us shift how we might approach the integration of computational thinking into our students' work? So that's our reflective big picture questions just to take away and mull over. And I hope I can work with you again in person. Just go to erlc.ca, just search my name or I'm teaching computer science, and you should be able to find a session that you can attend. And I'm looking forward to exploring this some more with you in the future sessions. What I'm hoping to do is to tap the shoulders of teachers I know who are doing great work integrating some of the concepts in the new curriculum already into their teaching and learning. And if I can bring them in and interview them so that you can hear stories of what they're doing, some of the strategies they found successful, some of the lessons learned that they've had so far, and some of their own next steps on their own journey. I think that the way we can learn from each other, from others that are in the classroom as well, I think that can be really powerful learning, because this is new for all of us. And the last thing anybody wants is a checklist like, oh, I got that part done, right? What we want to do is think, okay, let's all dig in and learn this together and develop a real interest in looking at things in new ways and reframing things we already do with some different vocabulary and moving things forward so we can really prepare our students for the world that awaits them. Thank you.